Okay. So before we talked about homonuclear coupling, so this is basically coupling between the same nuclei. Proton-proton coupling was obvious one. And then when we started the carbon NMR stuff, we actually talked about the fact that carbons and hydrogens do couple with one another. But what we do is we typically decouple the proton spectra because it has a number of benefits. Or so we decouple the carbon spectra, decouple the hydrogen of the carbon spectra because it has a number of benefits. Makes this NMR more simple because everything shows up as a singlet, but it also provides the nuclear over-Hauser enhancement for CH3, CH2s, and CHs and that sort of stuff. There is some other sort of homonuclear coupling, and a popular one is the fluorine. It's NMR active, and it couples with both carbon and it couples with hydrogen. If you ever have fluorine on in your molecule, it's interesting. It's very interesting, actually. Okay, so the coupling constant, little j, we know that this is measured in hertz, and it is the same value regardless of the NMR's field strength or operating frequency. So when you get up to, too bad I don't have a little, so when you have like a 60 megahertz NMR, like a quartet could sometimes look really, really big. And when you're running the same spectra on a 400 megahertz NMR, the quartet could be very close together. The chemical shift here, this could still be 5 ppm. This would still, the middle be 5 ppm. The difference is that on a larger field strength, now 7 hertz, if the coupling constant here was 7 hertz, this takes up far less width, I guess, on the x-axis, whereas on a 60 megahertz machine, it would take up more. And you see these really large sort of coupling constants. So on a lot of the older spectrometers, you'll see really big sort of peaks like this, but that's because 7 hertz, if that was a coupling constant, just takes up more room because we're working at a smaller field strength. Now, when we're talking about coupling, we use a little symbol here, 1 or 2 or 3, to basically depict the number of bonds that between the nuclei which are coupling to one another. Oh, I guess the thing which I forgot to mention here, it's actually the bond angle which is going to influence the value of J. So we're going to see that in a second. So when carbon's bonded to hydrogen or carbon's bonded to fluorine, directly bonded, it'll be a J1 coupling. When, say, a proton is on a carbon and these two protons are unequivalent, they're coupling together, this would be a J2 coupling. So a geminal, because they're twins on the same carbon. And 3 bond coupling, this would be our classic coupling where you would be seeing the number of neighbors, 1, 2, 3. So I think we basically, I covered at least a little bit of this before. Now the mechanism is a bit complicated. Dirac, basically we're using the nuclear spin model. We're not going to get into that because that's above our pay grade for what we're doing in this class. But the thing which is important is that typically the coupling will decrease as the number of bonds increases. So the further and further away, that value will typically get smaller. And when you've got, there's such thing as 4, like J4 and J5, these are what we call long range couplings, and we'll talk about, give some specific examples about that a bit later on. Okay. Oh, I guess I got to clear all of this. Okay, so J2 coupling. So the magnitude of a geminal coupling between, say, two, so carbon here, proton, proton, is really dependent upon the bond angle that this, I guess they call it the alpha angle between these nuclei. So when the angle is large, like 120, the coupling constant tends to be quite tiny. So an example of this would be if you've got a protons that are on a sp2 hybridized carbon here, sp2. So the bond angle here is approximately 120 degrees. And you'll see for that, that this value here is quite small. Sometimes you see it like if the coupling is actually, if the Hertz is 0, yeah, you're not going to see any coupling at all. So when it's quite low here, and the if it's in the 70 to 80 degree range, sorry. So what's the bond angle between two protons on a sp3 hybridized carbon? It's approximately 109, right? So 109 somewhere. It's funny that these J values are so high here because 109 gets you to around 15. So here we go, 109, somewhere in the middle here. So this negative sign for the coupling, that's just a consequence of Dirac's model when you can actually have negative numbers, but we don't count that. It's just, we would just say 9 to 15. So for two protons, it's around 9 to 15 Hertz. So geminal couplings between two protons on the same carbon tend to be quite large because 15 is one of the higher values that we will see. And there's some other values for some of the, like if you actually do have a radio labeled C13 or a phosphorus or a fluorine. Fluorine's got really large coupling values. But what we're really interested in is proton-proton. And so these are the two real examples of vicinal coupling, or sorry, geminal coupling. sp2 hybridized carbon or sp3. And so quite large coupling values for sp3, quite small for sp2. And it's based upon this angle. I guess the closer together that it is, I guess the electron density is supposed to be have better overlap, so the transfer of information can be better. Okay, let's clear some of this. So the moral of the story is the bond angle. As it gets smaller, the J values increase. That's the moral of that story. Stop this. So here are some examples. So the cyclohexane, cyclopropane, and then basically an alkene. And all of these fun examples. So cyclohexane, they've got a tert-butyl group here. The tert-butyl group is going to fix the conformation into this chair so it doesn't do an inversion. And that way, we're actually going to be able to see the different equatorial protons and axial protons. So they're going to have different chemical shifts. They're going to be unequivalent, and they're going to couple with one another. So this is just a nice little model to show that this bond angle is 109, and we get these large coupling constants. With the cyclopropanes, similar sort of thing, except for the bond angle is actually getting larger, and the coupling constant decreases. And then even larger, 120 degrees, and it tends to be quite a small coupling. And then I guess you can use this for determination of different diastereomers. So here we've got the relationship between these two compounds is basically their diastereomers. And we've got basically we've added a vinyl group on the beta carbon to this ketone. And what has happened is that when they did this reaction, they isolated two products. They could separate them because they're diastereomers. And then they wanted to determine, well, which one is which? Because this part of the molecule would have been fixed, and they were trying to figure out, okay, well, do I have the allyl group up or the allyl group down? And they were using NMR to determine which one it was. And they're basing it upon these two protons. So they would have had to do a couple of things here. They probably modeled this to see what it looked like. And in one of the two, this bond angle would have been larger, I guess over here. And so the coupling constant would decrease. It actually wasn't too much, but notice that the J value dropped by 2 hertz. So yeah, coupling constants are used quite a bit to determine between different stereoisomers. Well, in particular, it would have to be diastereomers. So it's one of those things where it's used quite a bit. I should have there was a really neat example back when I was doing my PhD. Let me see if I can draw. Can you see that?
Yeah.
Okay, good. So long ages ago, let's do a trip down memory lane. Let's do a trip down memory lane. Yes. Okay, so yes. And this was an ester, CH2. And yeah, these were OR. So a long time ago, there was a reaction that I was working on, which was this Diels-Alder reaction, where when this thing was all said and done, we made a I think I'm missing a carbon. Let's see here. Let's do this in 2 steps. Erase something. Okay, so what do we do? This goes here, this goes here, this goes here. There is a relative point to this whole mess. Okay, so I'm missing a carbon on that guy. CH2. This was like that. And then this would do a Diels-Alder reaction there, and this would give us something which looked like this. That's better. Okay. And we would have our CO2 ethyl here. O ethyl. This would be a double bond. This would be a OR. Now, it just so happened that the way that this worked was that we could get 2 different diastereomers here. One, we would have an H up, and if this H was up, this H would be up as well. And this H would be up. Or we could get it the other way around, where, and it's really important, the only important part, I guess, of it is this ring over here. If this was up and this was down, and this would be down as well. If my memory is correct. So there was this proton here had a relatively, actually no, it was this proton. This proton here, let me erase this other one, had a relatively, oops, draw. Because it was in between these 2 oxygens, it had a relatively high chemical shift and it was by itself. And so, and this reaction wasn't as selective as what we were hoping for. It actually made more than, that was part of the problem. It made 4 different, the first time we did it, it made 4 different diastereomers. And the interesting part is that I was able to actually separate them out. So we had, you know, A, B, C, and D. It was, gosh, it was a lot of work. But anyway, this proton here, in some diastereomers, it was a triplet. And in other diastereomers, it was a doublet of doublets, based upon how it was interacting with these 2 protons next door, because it has 2 neighbors. And were these 2 protons, they weren't equivalent to one another, because it was a ring system and all this sort of stuff. But just so happened that in one of the diastereomers, the coupling constant between this proton and these 2 was identical, so it would show up as a triplet. And in the other diastereomer, they were quite different, so it would show up as a doublet of doublets. And so when I separated out the thing, the one that we wanted was, you could tell immediately, because when I isolated the thing I wanted, we got an X-ray crystal structure of it. And then when we ran the NMR, it was a doublet of doublets. It was just a beautiful doublet of doublets. And every other example I did, which was the wrong diastereomer, it always showed up as a triplet. So you could look at the spectra and immediately say, oh, if it's a triplet, bad. If it's a doublet of doublets, good. And yeah, it was kind of funny, because when I went to my supervisor, say, oh yeah, figured this out, and sure enough, we've got the major product is exactly what we don't want. Then we had to change a bunch of other stuff, but that's the moral of the story is you can use coupling constants to determine between different diastereomers. It's quite a routine sort of thing. So that's what this slide is trying to basically depict that. And in this case, they're actually looking at the two protons that are on, like the coupling of those two protons, and they would be in a relatively interesting area, right? They'd because there's no neighbors on this side and there's no neighbors on this side, they should both, and they're only coupled to each other, they should only come out as doublets each. And so this coupling constant B would be an interesting way of determining the two diastereomers. So that's what that's all about. Okay, now the part at the bottom here is about when the n+1 rule actually functions. So remember, the n+1 rule is actually the 2i n+1 rule. Protons have an I equal to 1/2. So 2 times a half is 1. That's why this thing works out. But if you're using deuterium and stuff and you're looking for coupling, deuterium's has got a I of 1. So its splitting is a lot larger than that of protons. You get more multiplicities because the I is different. Okay, so I think before we were talking about if something's got a plane of symmetry, there'd be no splitting. And if you've got free rotation around a bond, so there's free rotation here, so these two H's shouldn't couple with one another because there's free rotation. In these examples, it's funny, this example here, there has to be something somewhere else. It sort of, because this would be, there'd be a plane of symmetry on this molecule here. So wherever they got the data from, there's got to be some other substituent somewhere so that they actually do couple with one another. But in this case here, there is no plane of symmetry necessarily within the molecule in the sense that this is like conformationally rigid. And so these two will couple because they're not equivalent. One's equatorial, one's axial. Okay, let's see here. Right, so with J3 coupling, this is our vicinal coupling. So this is the most common one for the n+1 rule to work. It's interesting, the coupling for this is really dependent upon the way that the orbitals overlap with one another. So if we draw a Newman projection of our two molecules that are coupling, we find that there are maximums when the two protons are anti to one another. So this is what this would look like, 180 degrees. So anti, this is a maximum. And the other maximum is when they are straight up eclipsing one another. This would be another maximum. They're at a minimum when the two of them are actually at 90 degrees. So if you had and usually we don't draw our Newman projections at 90 degrees, but if this proton was HA and HB at 90 degrees, this would be a minimum. And the theory is that if information's being transferred through the electron density of the orbitals, that when they're eclipsing, you've got maximum sort of information transfer, for lack of a better word. And when they're anti, the orbitals themselves, the filled sigma orbitals aren't interacting with each other, but the sigma star is interacting with the sigma orbital. So that's what this is trying to suggest. So the sigma star of this, it would be here, and the sigma star would be over there. So that's where those two are. Now, for a lot of our, if we had like a straight chain molecule, X, and there's free rotation, so this is rotating freely, then it works out to be the average of all the coupling constants, which tends to be around 7. So when there's free rotation, most of the free rotating systems, the J3 is approximately 7 hertz. It seems to be the magic number for that. So what's interesting is that Karplus did they generated a curve of the this bond angle between HA and HB, and there's basically a maximum at 0, so when they're eclipsing, and at 180 degrees there's another maximum when they're far up, when they're anti to one another. And then the gray area here can be the coupling values can go up if certain things like the bond length is shorter, so that's what this is trying to depict here. If it's compressed somehow, if the bond angle is actually more straight as opposed to being like lying flat, if they're pushed up somehow, and then the presence of negative substituents can also increase it. So this Karplus curve is interesting. So if you're at 7 hertz, it's somewhere in here, 50 degrees. So when you draw this, and it's at around, like a typical staggered conformation is around 60 degrees, right? So it's somewhere. So that's why you see most of these coupling constants between 6 and 8, because it's in this sort of range where if this is spinning around, the average, the minimum will be, the minimum actually would be 60 degrees, like from a steric sort of perspective, but it's going to be in that range between 40 and 60, and that's why these coupling constants tend to be around 7 when it's free rotation. So this there's a Karplus equation which goes with this, which you can plug in the data for, which is well above our pay, what we're interested in. But it's just interesting that, so you can, if you've got a conformationally rigid system, you can use the coupling constants and this curve to determine, are the protons eclipsing one another? That would be a high. Or are the protons at 90 degrees? That would be a low value down here. So yes, this dihedral angle is important. So it's a really neat little, it's a really neat thing, a real neat, it's incorrect English there. It's a neat equation which actually will explain quite a bit. So I would be negligent in teaching this class if I didn't bring up the Karplus equation or at least the Karplus curve, which is a graphical depiction of the equation. All right. So here are some examples. So again, we put a tert beetle group on to fix this in this conformation. And then when the two groups are axial, so they're diaxial, the bond angle is large. And so this coupling constant should be big. So between 10 and 14. When you've got an axial and equatorial, the bond angle is 60 and the coupling values are smaller. And then another example is when the two groups are both equatorial. Again, this dihedral angle is 60, and the coupling constant would be smaller. So in this, at least in this scenario where the two groups are axial, it's using this information, it's easy to tell this diastereomer compared to the other two, because just by looking at the coupling constants between those two protons. I guess this one doesn't actually have a Y. I should put a Y here. So if this was one diastereomer and this was the other, you could tell just by this coupling constant which one was which is kind of neat. Similar sort of situation here with the cyclopropanes. If you're looking at HA and HB, when they're eclipsing, this should be a maximum. You get a high coupling constant. And here, this is also it's not 180, it's 120, and the coupling has decreased. So let's go back a slide. This would be over here somewhere in this range. And this is just another example of something similar here. So what do you need to know for these two things? Basically, what you want to know is that for J2 couplings, it's dependent upon this angle between the two protons. And so for sp3, where the angle is 109, versus sp2, where the angle is 120, this will be higher. Larger J values, this will be lower. In the case of J3 couplings, yeah, I guess the main point we want to realize is that if the two protons are 90 degrees from each other, this is going to be a minimum. So the J value will be really low. And if they're either eclipsing or if they are anti to one another, where it's 180, both of those will be maximums. And so there's not a whole lot of ways to test this, except for drawing little cyclohexanes and just asking people to predict what the coupling constants might be. Maximum, minimum, how you distinguish between the two. Now as I said before, there is something called long-range coupling, and this happens a lot with double bonds, alkenes and alkynes. Yeah, it's quite a common sort of thing with alkenes and alkynes. And what's interesting here is that if you look at the J4 maximum versus the J4 minimum, so there's 4 bonds here. 1, 2, 3, 4. 1, 2, 3, 4. It's the interesting thing is that what does this, if we weren't talking about coupling constants and I had drawn this structure right here, what would I be trying to depict in my organic 1 class? Which ironically we did today. But today in class, we did it with regard to carbocations and carbocation stability, where electron density here was donated through space to stabilize that positive charge. This was called,
Hyperconjugation?
right, hyperconjugation. Well, it turns out that when we get to alkenes and alkene stability, there's hyperconjugation into pi systems too. So what this is actually, if you notice that the proton here, which would be on the bond, which is hyperconjugating that double bond, is coupling to the protons at the end. So, and then when it's 90 degrees to the electron density here, it's at a minimum. So J4 coupling is common when protons are part of the bond which hyperconjugates to pi systems. And so it's the same thing with triple bonds here. So this proton here is lined up with that orbital, so it's basically donating to that proton over there, coupling with that proton over there. So alkenes and alkynes can have long-range coupling based upon this sort of hyperconjugation, really, for lack of a better word. But the coupling constants aren't particularly large, so you don't see them unless you're using a really, really powerful spectrometer. And then there's just a whole bunch of other examples where this is via J5. Again, it's 1, 2, 3, 4, and then this bond here, 5. So hyperconjugating to and coupling with another proton, which could be involved in hyperconjugation. Minimum, where this is not in the plane. So you don't see that really at all. So yeah, so when you've got pi systems, you can sometimes see really, really long range splitting between protons that are far away. This is far more common, like seeing the proton next door, 1 Hz, something like this. So 1, 2, 3, 4, J4. W coupling is a bit more of a, tends to be, there's some which is actually quite large, but it's really interesting that it shows up when it looks like W's. And there's quite a few examples where there's long range coupling with W's. And the theory is that there's good overlap here because of this dihedral angle, and then there is good overlap here in the pi to pi star sort of orbital. That's what that's trying to, I think that's what this diagram is trying to depict here. But you'll see that most of these values are quite small. This one's actually quite large. Yeah, this one is 7 Hz is enormous for a W coupling. Okay, any questions on, like, you don't need to really worry about W couplings for like on a test or anything like that, but I think I'll try to give you an example of a long range coupling maybe we'll do one of these in class next week, an example where you can see long range coupling. So that's something to keep in mind. Any questions so far? Okay, now we sort of did this before, a little bit before, about chemical equivalence. I don't know if we talked a whole bunch about magnetic equivalence, but this is what we will do that as part of this. So If we have acetone, there's a plane of symmetry. The 3 protons on one side of the carbonyl are exactly the same as the protons on the other side of the carbonyl. They would react the same chemically. There's a plane of symmetry here, and so they should have the same chemical shift, so we would say that they're basically magnetically equivalent. So when protons have the same resonance frequency, they are magnetically equivalent. There's also, we can have planes of symmetry, or actually axes of symmetry as well. So this one's got a C2 symmetric, so you can flip it 180 degrees and you're going to get the same thing. This one's got a plane of symmetry right down the middle. What becomes interesting is that on aromatic rings, so we were kind of cheating before when we said that things were, well, they are chemically equivalent, but they're not necessarily magnetically equivalent. And so this is the point which we were, so when we were first talking about, say, an aromatic ring here, we had a substituent here, X, we had a substituent here, Y. And we would label this HA, and then over here, I'd label this HA primed, HB primed, HB. Now, the reason why I called them HA primed and not just HA is because of long-range coupling, and this complicates things. And basically, because of the long-range coupling, it makes HA and HA primed not magnetically equivalent. So to be magnetically equivalent, protons must be isosynchronous, so they have identical chemical shifts. That's typically not a problem. But the second part sometimes is, have equal coupling constants to all other nuclei in the molecule. This is where the problem arises. So the coupling constant between HA and HB, this might be 6 Hertz. HA prime, though, can undergo long-range coupling, 1, 2, 3, 4, 5, so at J5. And its coupling constant is probably going to be 1, if that, or less than a Hertz. And so because HA has a different coupling constant to HB than HA primed, they're not magnetically equivalent. So they might be chemically equivalent, but they're not magnetically equivalent. And so what happens on our spectra, and you'll see this on the proton NMRs that we did, like this should appear as a beautiful doublet of doublets, right? Where HA should be 1 and HB should be the other. They should both integrate to 2 protons, and we're happy. But because of this coupling constant difference, you'll often see little side things on your spectra, little side spinning peaks, and the doublets just aren't perfect at the way they should be. And this is basically a consequence of the fact that they're not magnetically equivalent to one another. So one coupling constant is large, the J3, and one is small, the J5. So they're not what we call magnetically equivalent. This is another example here. So HA would couple to the fluorine. One would be a cis coupling, one would be a trans, so they wouldn't be the same. Now, if you've got free rotation, then this doesn't become a problem. So just like all these would be chemically equivalent and magnetically equivalent, so would these, so would these. So when there's free rotation, it's not a problem because but it's when things have a locked configuration. So the most common example we would see is an aromatic ring. And if we were to somehow, if we were to lock, actually, I don't know how would I do that? Yeah, if we were to freeze this cyclopropane, just freeze it, and then so it couldn't rotate, then we would have problems, because HA would have a different coupling constant to B and then HB primed. But when we're running our spectra at room temperature and all that sort of stuff, and there is for free rotation, this isn't a problem. So question, which coupling constant should be bigger, the JHA HB or the JHA HB primed? Which one should be bigger? Right. Second one. This one should be larger. The coupling constant between HA and HB primed. And that's because this bond angle is 180 degrees. And so it's at one of the maxima for the coupling, for the J3 coupling. This one's at around 60 degrees. No, what is that? 30 degrees. And so that would be, should be lower. So, right. So this one would be larger. But, and then the other thing which would happen here is that these two, because you'd locked it, these two would actually start to couple with each other. But that's outside of what we're doing. So as long as there's free rotation, you don't have to really worry about this. But I just thought I'd bring up, so HA and HA primed are not magnetically equivalent because they've got different coupling constants to other nuclei. And it's a consequence of the fact that it's in a fixed location and there's no free rotation. Okay, now this is a review as well, right? We did homeotopic protons, and we did enantiotopic protons, and we did diastereotopic protons, right? We did our little let's say we had chlorine and we were looking at the two protons right next door to the chlorine. What we would do is we would replace, actually this is no, that's a bad example. If you wanted to tell, like these three protons on this terminal methyl group here, if you wanted to determine if they're homeotopic, diastereotopic, or enantiotopic, you basically replace two of them, or one at a time, with an X, right? So X, Cl, or let's use this one. And you compare these two structures to one another. I shouldn't have drawn the resonance arrow, but anyway. You compare the two. If the two molecules are basically identical, which they are in this case, because all you need to do is rotate this bond and then this becomes that. Then they are we call those protons homeotopic, and they are always equivalent in NMR. If we were to have changed, like picked the two protons here, and we were to swap them out with X's. And we compare these two structures to each other, we would see that they are mirror images, non-superimposable, which would be enantiomers. And so we would call those protons enantiotopic, and they would be equivalent except in a chiral environment. So if you were using a chiral solvent, or it was I don't know, complex to another chiral molecule or something, it wasn't in the chiral, they'd be equivalent. Now, diastereotopic protons, however, they are not equivalent and they're not isosynchronous. So they can be split with J2 coupling. Now, on some occasions, they might coincidentally do this, but often they're not equivalent and they don't have the same coupling constants. So they will couple with one another, which is interesting. So, and in the case here, there has to be a stereocenter, which is chiral next door to it. That's the point. Oh, so what they were doing here is they're swapping out the H with an A. I was swapping it out with an X. But anyway, so it needs to contain a stereocenter of some type. And I think there's some nice little spectra on the next sheet, which we'll talk about that. Yeah, let's clear this mess. So this is a carbon NMR. And it's drawn really funky with all of the protons attached to it. But let's draw it without the protons. So this is carbon 1, carbon 2, carbon 3, carbon 4, and then carbon 5 and 5 primed, we'll call it. So and what you see here is that when we look at the carbon spectra, we've got carbon 2, which would be the one at 60 because it's the most deshielded. It's next to it's attached to the hydroxyl group. Here's carbon 3, and then 1 is way over here, and 4 is right next door. But you'll notice that carbons 5 and 5 prime each have their own individual resonance because they're not equivalent because of this chiral center. Now, if we were to oxidize this to the carbonyl, then they would fold into one proton because they are now, there's no chiral center, so they become homeotopic. Yeah, they would both be the same. They'd both be identical. So it's one of these interesting little things. So once you put a chiral center in here, now you see the two different carbon 5s because they're now become distereotopic. So I've drawn this without, yeah, so that's interesting. So let's look at the proton NMR because that's the one which is the most interesting here. And we'll redraw our compound. So the 3 protons on this carbon here are going to be equivalent. And so CH3, right. They're going to be equivalent, so they're going to appear as the same. Over here, you'll notice that they're a doublet, right? A really fine doublet. That's because they're coupled to this proton right here. So it's a doublet due to coupling. And we've got C5 and C5 prime. They are both, they come out as doublets, and they integrate to 6. So 6H, 3H. Because again, there's a proton right here, which they're coupled to. So one neighbor is going to be a doublet. But the 2 which are really, really interesting are these 2 protons here. And you'll notice that they don't even have the same chemical shift. They are quite different. Chemical shift is different, and they're going to be coupling with one another, which is going to give them a really large coupling constant. HC here, this is quite a complex splitting pattern because it's coupled to 4 protons on one side plus 1 and 1. So that's going to be, we've got an expanded version of this in a second, but it's really neat that these 2 peaks, HA and HB, are got completely different chemical shifts, and they're going to have a large coupling constant. Now let's look at the expanded version of this. Right. So you see this pattern here. Laser, where's my laser? 1, 2, 3, 4, 5, 6, 7 peaks. And you'll notice that this peak, this peak, this peak are relatively the same size. These 3 are slightly taller, and this one in the middle is the tallest. But it doesn't fit at all with our Pascal's triangle of how coupling works. And over here, you see a very similar pattern as well. 1, 2, 3, and then a bigger peak in the middle, and then 3 smaller peaks on the end. So there's 7 peaks, but they don't resemble anything. Over here, HD, which I think was this guy here. This one looks a bit better with regard to Pascal's triangle, a tiny peak here, slightly larger, slightly larger, slightly larger. But there's all these little side splitting peaks here. So this, we're going to see in a second. This is what we call second order second order coupling. And it's a real mess to try to analyze. It's a real mess. So often when we're putting together some like practice questions stuff, having peaks like systems like this on there makes analysis really, really, really hard. But the funny thing is that this is the common thing in NMR, and the N+1 rule where everything fits nicely is far less common in for complex molecules. So, right, so the splitting. So here are 2 splitting things back here, 4.1 and the 1.23 or wherever it would be. So the coupling constants in each of them are very similar. So we've got a large coupling value here, which is going to be the 13.7. Then there is another, so if you're HA, you've got this large coupling constant. Then there's another coupling constant here and another coupling constant here. One of them is 8.3, one of them is 5.7. And so I guess the 5.7 is to here, 5.9, sorry. And this one would be the 8.3. And so it's basically what we call those splitting trees. And coincidentally, the way like 1 to 1 to 1, and then this peak here was where they sort of came in together, which would make that 2, 1, 1, 1. And it was similar over here as well. Larger peak in the middle, so 1 to 1 to 1 to 2 to 1 to 1 to 1. So this is technically a doublet of doublet of doublets, because all of the J values are not the same. So a doublet, and these can be, so this would be the same as a quartet, because a quartet is a doublet of doublets, and then divide that again, of doublets. But because because they were feeding into one another, it comes out to be looking like a quartet, because it's 1 to 3 to 3 to 1. So a quartet's technically a doublet of doublets, but the coupling constants are all the same. This is a doublet of doublets where all the coupling constants are completely different. So actually, technically, this isn't a second order spectra. We'll get to that in a second. So n+1, when you've got free rotation, this applies, and all of the coupling constants are going to be the same. So the coupling constant between HC is going to be equivalent to HA and HB. So that's what this means here. And because of this free rotation, A and B aren't going to couple with one another. But when you don't have free rotation, then the other factor rolls in, is that HC, one J value will be different than the other. So AC does not equal BC. And then when that happens, these two start to couple with one another. So you get the J2 coupling and then two versions of the J3 coupling. So restricted rotation. And here's another example, an epoxide. And so this will couple here and this will couple there. These two will couple. So each proton, C, B, and A, are all going to be doublet of doublets. And the coupling constants are all going to be slightly smaller. So you see three different doublet of doublets here. And one of the things that, so the coupling constants between the three, so this will be one coupling constant, and this will be the other. This will be one coupling constant, and this will be the other. This will be one coupling constant, and this will be the other. That's basically the way it works. And so this one here between the two, this will be the same over here. So this would be the same over here. If you ever have a, if you're ever given a spectra and you're trying to just do trying to figure out what might be coupled to what, there's a neat trick you can do, and that is just grab a little piece of paper and put the edge of the paper right at the two peaks and just draw on the piece of paper. So, and then move that piece of paper somewhere else on the page, and then you'll see, oh, that peak there and that peak there have got the same width. So I know that this is coupled to that. And if you draw, like, so for a larger coupling constant between here and here, your piece of paper would have lines here and here, and you can move that over and see that looks like that would probably be the same as between here and here, I think. I might be wrong. But in this case here, they've given you the values up here in hertz. So you can actually just subtract 1 hertz from another and see what the coupling actually is. Like on the example with the long range coupling, there's some hertz values, and we'll do some calculations for that next week. So, but these would all be, so this would be JAC, JBC, JAC, JAB. This transcoupling constant is probably the largest, the AC. So this one will have it, and this one will have it. That's this big one between here and here. Interesting. Okay. Yeah, this is basically saying how to calculate the 2 coupling constants here. So the first one you can measure between, so this large coupling constant J1, that you can either do it between here and here, or it's the same as going between there and there. And the smaller coupling constant is the edges. They're going to be equivalent. And when you do the calculation for coupling constants, one might be 7.2 and the other one might be 7.3. It's really 7.25, and if you round up, it's 7.3. So just keep that in mind. And here is another example of just calculating the coupling constant. So the J1 for a doublet of triplets between the 2 center peaks, that's the easiest way to do it. And the smaller coupling would be between the center peak and the 2 side peaks. And here's our doublet of doublets. And the large coupling would be between there and there, or between there and there, or between there and there. So there's lots of places where you can actually calculate the various, let me erase that, coupling constants from erase. Oh, I must be writing on I'm writing on my PowerPoint. Okay. Today has been chaos. Okay, now this is where I wanted to get to. Let's see, we've got 30 minutes left. Okay, sorry for burning through all this. Okay, so second order spectra. Okay, this is interesting. Okay, so a really fascinating thing happens when, if you've got 2 protons that are, let's say, they're geminal protons to one another, and there is some chiral center close by, so they're distereotopic, and we'll call this Y. And so they are going to couple with one another. So they're going to have a J value of approximately 15 hertz. So it's quite a large coupling constant. Something really strange happens when the chemical shift of those protons is very similar. So the chemical shift is close to one another, but the J value is large. Then you get what we call the strongly coupled or second order spectra. So this is what this is trying to depict here. So the chemical, this is supposed to be the chemical shift, and this is the J value. So the chemical shift is similar, and the coupling constant is big enough that it's close to this. In spectra where the chemical shifts are quite different, are very large, then, and this is still, it doesn't, this will be a typical first order spectra, what we normally see. But these, when you've got similar chemical shifts in large coupling, we call these second order spectra or strongly coupled spectra, and they make some really, really interesting patterns. And it says here they look deceptively simple, but measuring their J values isn't something that we're ever going to do in this class because it is quite complex. The best way to show this is with some actual, with some data. Oh, we'll come back to this in this. Let's come back to this in a second. Okay, so here we've got 2 protons, and then this example here, it's a J3 coupling. So they're on neighboring carbons, and the chemical shift is large. So if this is HA and HB, so we'll call this A and B. Each would just be one neighbor, so this would be a doublet. And so you'd see a doublet here and a doublet here. All good. Now notice what happens when the chemical shifts of these 2 protons start to get closer. So here it still looks like a doublet and a doublet. And now they're getting even closer. J, chemical shift of A, chemical shift of B, still 2 doublets. And you notice they are, the peaks are starting to, they skew towards one another and they're getting closer to one another to depict which direction what they're coupled to. And then when the chemical shift is really, really close, you make this thing. What does this look like?
Quartet.
Yeah, it looks like a quartet, right? So this looks like a quartet. And really it's 2 doublets that have this, that have very large coupling constants, but are the chemical shift is very similar. And then over here, this one beneath it is even more extreme, and you can sort of see the little side peaks here. So a system which looks like this has got a name called basically an AB quartet. So if you ever hear the term AB quartet, this is what's going on. It's a second order spectra where the J values are large, but the difference in chemical shift is really, really small. And so this is what this, it's the difference in this really is what we're talking about, is difference in chemical shift here. Now let's go back to why this is called an AB quartet. There is a notation system called the Pople notation. And basically, protons are assigned letters like A, B, C, all the way down to, for whatever reason, X. And if only one proton is responsible for the signal, it's just called A. If 2 protons are responsible for the signal, you would call it A2. And if it's a methyl group, for example, it would be called A3. Now, let's say you've got CH3, CH2, chlorine. Or if you've got what would be another example, I don't know, good example actually. So if protons have similar chemical shifts, they are assigned letters that are close to each other. So on this next page, here's, because the two protons here, A and B, the chemical shift is so close. That's why they're assigned letters that are close to each other in the alphabet. Where we started way up at the top, where the chemical shifts were really far apart, like here and here, we assign them letters in the alphabet that are really, really far apart. So AX, because A is, I don't know why it's not Z, it's X. A is far from X, so those two chemical shifts are really far apart. A is close to B, so you end up with this AB quartet, because you get this quartet structure because of this second order spectra, and it's AB quartet. So in this molecule here, where this CH3 and this CH2, the CH2 is right beside the chlorine, we would expect the chemical shifts of these two protons, we'll call this one A3, and this CH2, because it's beside a chlorine, it's probably going to be quite far from that A. So we would call this system an A3X2. So all first order spectra, which we were dealing with in the past, would be AX systems. And when you get protons that are close to each other in chemical shift, but have large coupling constants because they're like diastereotopic or something, these would all be AB systems. So second order spectra are all AB systems. And this, if we go back to the next slide here, what happens if they've got the exact same chemical shift? Then they're identical, right? So they just become an A2 system. So this would be a first order, technically this would be a first order too, but in the middle, there's these second order spectra where things are interesting. So the Pople notation is basically supposed to depict all of these sort of systems. So if you have three protons and they're all have very different chemical shifts, like for example, CH3, CH2, CH2, chlorine, we would call this A3, M2, X2. Because M's in between A and X, so we would expect these to be different. But if you have a long chain where they're starting to merge into one, then you would call this, you could have an AB sort of ABC system where they're all very similar. And here's where we get the aromatic protons, where the A prime, B prime, or A primed, X primed. So the para-substituted rings are, it depends upon like how close. So yeah, you can get second order spectra for the aromatic rings as well. I can't remember how I ever asked this sort of stuff on a test before. I don't think I did, if you're worried about that. But it's really neat. Like this, there's some really fascinating systems here. So this is a, and there's two of these, so this would be the X2. So a doublet and a triplet. That would be our first order spectra, which would be interesting. Now, when you're going down, moving closer, if these two protons here are unequivalent and they couple with one another, then this would be a doublet of doublets, and this would be a doublet of doublets too. So that's why you see here a doublet of doublets The peak heights are a bit strange, but they're skewing because they're coupling towards one another. And then when you get, and as the chemical shifts gets closer, so it's an AB2 system, then you're left with this undecipherable undecipherable mess, right? And then it may get really close and you end up with a system like this. So second order spectra have got some really, really interesting, they look interesting. And here's another example. So two triplets, A2X2, chemical shifts are far apart. Coupling is relatively small compared to the difference in chemical shifts. And as they get closer together, where the chemical shift would be very similar and the coupling is very large, then you get to systems that look like this. And when you get even closer, something like that. So there's all these wonderful things that you can look forward to when you've got some pretty complex molecules that have protons that are unequivalent, have a large coupling constants, but their chemical shift coincidentally is quite close to one another. You get some very bizarre looking spectra. So that's basically like Pople notation and what you see in some second order spectra. It would be completely unfair to try to sort of solve, to give anybody something that looked like this. Like, how in the world would we ever solve that, or any of these? So, but the thing to keep in mind from today's lecture is if you've got diastereotopic protons, they're going to couple with one another, and they're going to have large coupling constants because they're geminal, and they can have they can be quite far apart. And so I guess, what am I trying to say here? Let's go back. So here is an example. So these two protons, B and A, they are diastereotopic. They couple with one another. They've got different chemical shifts. One is trans to the aromatic ring, one is cis to the aromatic ring. And so they come out with different chemical shifts on a spectrum. And the other example was that here, the two peaks they've got different chemical shifts, but they're attached to the same carbon. So that's when you've got diastereotopic protons, they can have different chemical shifts. But they're coupled to one another. So I guess that's the key point. I think that, yeah, that's the one thing I wanted to, for this interesting sort of, and I wanted to give you a flavor of what happens in a second order spectra too. That was why we did this today too. So what we'll do, I'll dig up an example of long range coupling that we can look at on Tuesday. And I think on the same question, I've got another one which has diastereotopic protons, which have different chemical shifts. And we can look at that and maybe calculate out some coupling constant just so we know how to do that. And then I guess the last little section will be we'll just do one lecture on UV visible, I guess next Thursday, I guess that would be Thursday. UV visible isn't used much in organic anymore unless you've got conjugated a conjugated system, say something like, but it is used a lot in organic chemistry because of the transition metals and all that sort of fun stuff. You probably already come across it more in that already, I am thinking. But for most organic molecules, when we make them in the lab, they're pretty boring. They have no color. So yeah, it's only when you start to make conjugated systems where you can get some nice color and UV visible becomes useful. But we should at least discuss that a little bit because it's part of the domain of spectroscopy. Are there any questions? Okay, well, if not, what I'll do is we'll end early, and what I'll do is I will email everybody individually your midterm, so you can take it home and look at it. Overall, they were done extremely well, so that's good news. What am I doing here? All right, well, I guess that is, I will see everybody on Tuesday unless anyone's got questions or anything like that.
See ya.
All right, thanks.
Have a good weekend.
You too.